Hey everyone, in this video we're going to talk about gears in general and specifically gear train examples and a compound reverted gear train example. And we're also going to be introducing force analysis in this video. So this video is part of a lecture series on mechanical design 2. So if you haven't checked out other videos before that, please go back to the other videos. So to start this video on compound reverted gear trains, we're going to take a step back really quick and just look at one figure that might be important to solve problems in any problems that you would have from a textbook or any situational problems where you would have the following type of design. So we haven't talked about this yet, but crossed helical gears are helical gears that can be basically mounted at 90 degrees from each other. And each pair of drawings refers to a single gear set. So we have a pair of drawing and it's the same gear set for A, B, C, and D. And worm gear sets kind of work in the same way. So you can see that we have different types of designs. We have left-hand designs and right-hand designs. So the top designs are right-hand designs, and then the next ones are left-hand design. And essentially, it just gives us a rotation of a gear when the top one is going down. So for example, here, when the top is going down, the bottom gear that is at a 90-degree axis from it is going to be clockwise. Whereas here we have up would go clockwise and vice versa. So just a way of figuring out whether something is going clockwise or counterclockwise if we have this type of design. So sometimes in problems, you'll be tasked with looking at a problem, looking at a helical gear set that is connected in this way. And essentially what you need to be able to say is, well, I know my helical gear set is at 90 degrees and I'm told it's a left-hand design or a right-hand design. And based on the left-hand or right-hand design, I can go to this chart and make sure that I have the right number for this. So just a little bit of an aside, just to help with problem solving if you need to use this for problem solving. Now, going back to compound reverted gear trains, we had ended the last lecture in the series with a problem that we have already solved for a normal compound gear train, but we haven't done it for a reverted gear train. And so that was that if E is equal to 30 and we're supposed to minimize the size, so that means that we want to increase the speed by 30 times when E is equal to 30, then we're told to use a compound reverted gear train now to do so. And from a previous problem, we had already solved that E, to minimize the size, should be equal to 5 times 6. So we should have one set of gear trains that is equal to 5 and one set of gear trains that is equal to 6, so that we get, or our mg is equal to 6 and 5, so that we get a 30 output, essentially. We had also found that NP min, so this number right here, from interference, this is from interference, was equal to 16. And based on that, well, we can say that we essentially have 4 unknowns. And we have a certain set of parameters that we need to satisfy. And the 4 unknowns are N2, N3, N4, and N5. And one of the things that we know is that N2 and N3 are going to have an mg of 6. We're going to keep the same as our previous example problem. And N4 and N5 have an mg of 5. So mg being the gear ratio. So it's a number of teeth in the gear over the number of teeth in the pinion. And we had found out before that we had 96 teeth, 16 teeth, and 80 teeth, and 16 teeth for the previous problem. But the problem with that is that we also now need to satisfy the following equation. We need to satisfy that N2 plus N3 is equal to N4 plus N5 in order to design a compound reverted gear train. So if you remember, your compound reverted gear train looks something like this. So we have gear 2, which is going to be a big gear with a pinion 3, and pinion 3 is going to be connected to gear 4, and gear 5 is going to be a smaller gear, and this axis is going to be aligned with, sorry for the scale, it's not perfect, but you get the idea. So 2 and 5 would be aligned with each other, even though they would be on separate axles, and 3 and 4 would be on the same axle, and aligned with each other as well. So in order to satisfy this, we need to satisfy the equation in green. So the other thing that we know is previously the biggest gear was number 2, okay? So the biggest gear was 2, and we had come up with values for that. Now, if we test out our previous design, which had N2 is equal to 96, N3 is equal to 16, 96 plus 16 would be equal to 112, and that would not be equal to N4 plus N5, so it would not be equal to N4 plus N5 if we had our previous design. So if we look at this equation and we then say, okay, let's try and figure out what our number of teeth should be in order for N4 and N5 to be equal, and we know that we also know that N4 over N5, which is mg, should be equal to 5. So these are our two governing equations for this system. So if we were to solve for this system and find the right number of teeth for N4 and N5, we would have to say, okay, N4 is equal to 5 times N5, okay, if we rearrange the equation on the right. And we also have the following equation that says that we can then plug this in to here and say that 112 is equal to 5 times N5 plus N5, which is going to be equal to, we can say that 6 and 5 is equal to 112, which is 18.67. And then from there, we could do 5 times 18.67 and find N4. The problem is that we can't have 18.67 teeth. We can't have non-whole number of teeth. So this is completely wrong. We cannot do it this way. So we have to change our number of teeth in all teeth. We can't just keep the 16 plus 96 that we had before. So we're going to have to do a technique that's called normalizing. And obviously you can do this by trial and error, but it would take a really long time. So another technique that you can use is called normalizing. So if we look at our system again and our problem again, and we're going to normalize our values. So what we're going to do is we're going to do what we did previously in the problem and say, let's go back to square one and let's assume, even though we have already the knowledge that a one gear tooth wouldn't work because we have interference and we need 16 minimum, we can assume and normalize that N3 is going to be equal to 1, okay? And this is just a current assumption to find numbers, okay? So it's not the truth, obviously, but it simplifies our system to the maximum. That means that N2 is going to be equal to 6. And that means that if we plug it into our equation of N2 plus N3, we can now find the number for N2 plus N3 is going to be equal to 7. So we're basically simplifying to the lowest number possible. And that's going to be equal to N4 plus N5. Now, obviously, we know that that's not going to work, okay? Because N4 plus N5 would have to be equal to 7 as well, and would be very challenging to do that with a different gear ratio. So we can also write again that N4 over N5 is equal to 5 based on our mg for 4 and 5. And based on that, we can come up with the equation that says 7 is equal to 5n5 plus n5. And then we can go one step further. We can say 7 is equal to 6n5. And now what we can say is that n5 is equal to 7 over 6. Now this is going to be very interesting for us because now what we can say is we assumed that N2, so as an aside, right, we're assumed that N2 was equal to 6, N3 was equal to 1, N4, N5 were unknown at the moment, so N5 would be 7/6, and N4 will leave as is for now, okay? So if we have that, we could plug in then to find N4 if we wanted to, but we're not going to find it right now because it doesn't really make sense. Now, what we can do for all these to be whole numbers is we can say since N5 is the since N5 is the smallest gear on, or the pinion on the second rack, we know that it has to be a whole number. So the first thing we can do is we can say, let's multiply this by 6. And if we multiply by 6, N5 is eventually going to become a whole number. Okay? And by the fact that we developed this equation from N2 plus N3 is equal to 7, which is equal to N4 plus N5, it means that if we multiply everything by 6 in the equation, we will get a satisfaction of this top equation. So we will satisfy this equation if we multiply everything by 6 in this equation. And we're going to make it a whole number as well. So if we multiply N2, we get that N2 is equal to 36. If we multiply N3, we get that N3 is going to be equal to 6. Then if we multiply N4, I will do that in a second, N5 is going to be equal to 7. And essentially 6 times N4 is going to be equal to 35. So now we have a relation that has whole numbers between N2, N3, N4, and N5. And if we actually count up the sum of both sides, we get 42 and we get 42. So now we have whole numbers. Based on this normalization, we normalized everything as 1. Then we multiplied by the number to get rid of the decimal for N5, which is our lowest number essentially. And we got all whole numbers. Now, based on this, we now say, okay, 42 is equal to 42, therefore it satisfies everything. It satisfies our N2 plus N3 is equal to N4 plus N5. So we're good to go, satisfied. The problem is that it still doesn't satisfy our interference. So we know that our interference, we need at least 16 teeth. So now the next thing we have to do is, keeping these numbers fixed, what we can do is we can multiply all the numbers once again by a certain value. So we can see that to get to 16 teeth, we would need to multiply everything by 3. And if we multiply everything by 3, we end up with N2 is equal to 108, N3 is equal to 18, N4 is equal to 105, and N5 is equal to 21. And we can now see that this satisfies our N2 plus N3 is equal to N4 plus N5 equation, which means that it satisfies a compound reverted gear train. So if you were to design this system as a compound gear train without reverting it and without saving extra space, you could use 16 teeth for N3 and N5. Now, if you were to design it with a compound reverted gear train, you couldn't use 16 teeth. You would have to use 18 and 21 to make sure that all the teeth come out to the same number so that the diameters are aligned with each other. And that way you satisfy the alignment of both axles. Okay, I hope this makes sense. If not, rewatch this part of the video, and there will be some more thinking about that a little bit later, and you'll be doing a lot of example problems based on that. So moving forward, what we can do after this, there's many ways of getting to this number, but the best way is really to do this assumption of N3 is equal to 1, and then you start from there, essentially. You start with one side and you say, my lowest gear or my pinion is going to have 1, and that's how you normalize. Okay, so next step is we're going to learn about force analysis for spur gears. And we're going to focus on spur gears because spur gears are the easiest in terms of analysis and the easiest to understand in terms of forces. And mathematically, they're very simple. Okay, they're straight gears, they're spur gears, they have an angle that is straight, so it makes it very easy for force analysis. Whenever you go into bevel gears or helical gears, the math is a little bit more complicated, but the simple theory is pretty much the same. So we've said this before, but I'm just going to rewrite it. Whenever you number a system, numbering the system is going to be very important for force analysis. And we're going to talk about a little bit about the numbering system and how it works. So first thing first, 1 is always the frame of the system. So we always know that the pinion starts with 2 or the first gear starts with 2. The reason is because 1 is the frame of the system. 2 is usually the input gear. So it's the gear that's usually driven by a motor or by something, and it's the input gear. Then the other numbers, 3, 4, 5, 6, etc., are all the other gears. Okay, we just call them all other gears within our system. And they're usually in order. It makes sense to number them in order, just for simplicity. Now, the shafts, as we've already discussed, are A, B, C, D, usually lowercase letters. Okay, so we have shafts A, B, C, D, and we go from there for the shafts. Now, the notation for force is going to be very important, and it's going to be something that you're going to have to get used to as you go along once we start doing force problems in this lecture or the next video, I believe. So notation for force is going to be important, and it might take a little while, but hopefully it'll be clear and understandable. So we're going to write a few examples. F2 to 3. So F2, 3 is a definition, and it'll make more sense once we start drawing diagrams. But F2, 3 is the force exerted by gear 2 on gear 3. So how I like to think about it is I think of F2, 3 as F or force from 2 to 3. Okay, so it's a force that comes from gear 2 to gear 3. Okay, in the same way, we can also write a force between a shaft and a gear. So we can say F2A, for example, would be the force of gear 2 against shaft A. And of course, I can do the opposite of that too. So I can do FA2. And FA2 would basically be the opposite. And you could also write, if you wanted to, F32 would be the opposite of F23. Okay, so it would be the force exerted by gear 3 onto gear 2. Okay, and we'll talk a little bit about what that means and how that works. Now, we're also going to add, so we have these subscripts. So subscripts are under the letter. We're also going to have superscripts to describe the forces. And the superscripts are going to indicate direction. Okay, and they're going to indicate direction in the X, Y, Z direction, or alternatively in the tangent and radial direction. So we're going to be using tangential direction as well as radial direction. So for example, I could write a term for force from gear 4 onto 3 in only the tangential direction. So I'm writing the force in the tangential direction of gear 4 to 3. Okay. All right. So now what we can do is we can start drawing an example of a system put together and labeling it essentially. So let's draw a simple system of 2 gears. So we have 1 gear at the bottom and a bigger gear on top of it. Okay. And obviously the bottom gear is going to be called a pinion and the top gear is going to be called the gear. So we're going to have 2 and 3. We're going to call these gears 2 and 3. Okay. We're also going to write for our information that the Y direction and the X direction is like this. And inside those gears is going to be a shaft. It's going to be shaft A, shaft B. And we're going to say that our our pinion is going to be rotating at an angular velocity of n2. That means that, and it's going to be going clockwise. That means that this is going to be going to at an angular velocity of n3, which is going to be counterclockwise. And other things that we have to do, so we're going to draw a dotted line where we have the tangent to where the gears meet. So we're going to assume that the gears meet exactly vertically, okay? It's not perfect on my design, but they meet perfectly vertically, pretty much vertically. And what I'm going to add here is I'm going to add a line at a certain angle. And this line is supposed to be straight. And this line gives us our 20-degree line of action or 25-degree line of action, however we want to make the line of action. So usually it's going to be 20 degrees. If you don't know your line of action, I suggest that you guess 20 degrees. Okay, so we have this information now, and we have this drawing. So now what we can do is we can start doing a free body diagram, and hopefully you remember how to do free body diagrams. We're going to do a free body diagram of gear 2 and look at gear 2 and what's happening on gear 2 and how everything is working out. Okay, so there's going to be a few things that we have to take into account. So gear 2 is going to be driven by something. So we're going to add that gear 2 is driven. And we're going to draw a zoomed in version of gear 2. Okay, so this is gear 2, shaft A, gear 2. I'll put the 2 number here. And I'll put that it's rotating at a velocity of n2. And we're going to add forces to it. So I'm going to add all the forces in red so that we have them clear. And we know that the contact point with gear 3 is here at the top. So now, if the gear is rotating clockwise, in what direction do you think the force from gear 3 to gear 2 is going to be happening? So gear 2 does not feel any force that is transmitted to gear 3. It only feels a reactionary force from gear 3 back to 2. Okay, so if you think that the teeth of your gear, and this is where I'm going to try and show you with the highlighter, if you think that the teeth of the gear are, so gear 2 is pushing this way, okay, it's pushing clockwise, that means that it's pushing gear 3 in this direction, okay, in the direction of the line of action. That's the force direction from gear 2 to 3. And gear 3 is essentially resisting that force. So it's actually giving you a force that is in completely the other direction. Okay, so if you think of the teeth or the tooth of gear 3 and the tooth of gear 2, so this is tooth of gear 2 and then the tooth of gear 3, the tooth of gear 2 is pushing in this direction, and the tooth of gear 3, when it's contacted here, is actually pushing back in this direction. Okay, so we can add to our free body diagram that 2 feels a force of 3 onto 2. And let me put it in red because I said I was going to put it in red. So it feels a force of 3 onto 2 along the line of action. So along that 20 degrees. Okay, I'm exaggerating the degrees just so that it's easier to read, but essentially it would be at the 20 degrees. And this force has 2 components that we can add. So it's going to have a component in the x direction, which is going to be F32 tangent. Okay, that's a tangential component of the force compared to our circle. And it's also going to have a radial component, which is going to be F32R. Okay, then what are the other forces that are taken into account? So let's think about if we only had this force, and if we only had force 3-2, what would actually happen to our system if we only had force 3-2 and we had no other forces applied to the system? What we would actually see is that essentially our gear 2 would start moving towards the bottom left. So our gear 2 would essentially start translating this way. Okay, because it wouldn't have any way to hold itself. So that means that we need our shaft to be attached somewhere, and our shaft is actually going to create a force onto gear 2 to hold it in place. So we're going to have a force from the shaft that's going to be called FA2, okay? And FA2 is going to have a component in the Y direction and a component in the X direction. So we'll call this Y and X. We can obviously add as a superscript to FA2, but just in interest of space, I didn't put it. Now, the last thing that the gear also feels is because this is the driven gear and it's the first gear in the system, the gear also feels a torque from A to 2, from the axle to gear 2. So it feels a torque in the clockwise direction, and that's why it's rotating that way. Okay? So a few things that we have to think about and a few things that we have to understand what's happening. So we have to understand how the load is transmitted from gear 2 to gear 3, for example. So the transmitted load is going to be equal to WT is equal to F32 in the tangential direction. So essentially what we're saying is that we do have a line of action of 20 degrees, but the actual transmitted load between two gears is the tangential component of the gears, okay? And we usually call that W sub T, okay? In this case, in our free body diagram above, we can see that the useful transmitted load is actually F32T. And what we can write as well is that the radial component serves no purpose. So the radial component and the fact that we have an angle of attack or a certain angle doesn't really serve a purpose. The only purpose that it serves is for there to not be interference and for there to be a smooth transmission of power as opposed to just like one point on the gear hitting the whole time. So that's something that's important. Now, what we can do is we can start writing down some equations based on this free body diagram. So the first equation that we can write is what the torque would be equal to from A to 2 as a function of different things on the diagram. So the first thing we can write is we can say T A to 2, or the axle to 2, is going to be equal to D2 over 2, which is the diameter of 2 divided by 2, okay, or the radius, times WT. So if you think about that, that's just the torque is usually a force times a distance, and it's a force times the distance of where it's happening. So the torque from A, which is in the middle, to the outside of the gear would be equal to D2 over 2 times WT, which is equal to D2 over 2 times F32T. Okay, and we'll talk about direction of torque later on, but for now, we know the torque is happening. We know that that torque is usually happening in the same direction as the rotation of the system. Okay, so now we can look at power transmitted. So if we have a torque through our system and we've managed to write our torque in terms of force on the teeth, we can also write a power transmitted. And power transmitted is usually H is equal to T times omega, okay, torque times omega, which we can rewrite as W sub T D over 2 in general, okay, we're not going to write it for this specific problem, but that's going to be in general, times omega. Now, this can be calculated in kilowatts or horsepower. The only thing that's very important here is the units, and the units are a little bit complicated to solve. So we're actually going to be coming up with some equations that will simplify our way to find power. But it's always possible to find power this way. It's just you need to convert to radians per second, and you need to have the right unit for torque as well, which is not always easy to do, especially in US units. So another thing that we can write is that meshed gears in general have 2% power loss max. So that means that if you have a good set of gears, you're only going to lose around 2% of power from one gear to the next. So if you put a power of, let's say, 300 horsepower through one gear, the next gear will feel at the minimum 294 horsepower. Okay, and gear data is usually tabulated with pitch line velocity. So instead of using the rotational velocity, you actually use the pitch line velocity, which is a little bit easier to work with. It's a velocity in meters per second, and it's essentially the tangential velocity of your gear at the tooth. Okay, so if we have our gear set rotating around an axis, okay, let's say the axis is here, our pitch line velocity would be the tangential velocity. And we can say that the pitch line velocity is equal to omega times d over 2. Okay, and omega would be in radians per second and the distance in meters, and then you would get meters per second. Okay, now that's all well and fine, but it actually is a little bit easier if we come up with, instead of always having to convert to the most basic units, we can also come up with a way to calculate everything in terms of the units that we usually use for gears and for gearboxes, as well as the units for velocity that we use, like feet per minute and stuff, as opposed to having to do everything from scratch in terms of SI units and standard units. So in your formula sheet, and I'll show you really quick here in your formula sheet, which is right here, you have some equations here at the bottom with force analysis relationships. So all these equations are there for you already, but we're going to write them out now just to make sure that we have them all and we understand what they all mean. So going back to here, we're going to write first the US units equations. So in US units, we can say that V is equal to pi times d times n over 12. So instead of doing omega d over 2, we can do pi d n over 12, where n is in RPM, so we don't have to convert to radians per second. D is in inches, and V is in feet per minute. Okay, we can also write feet per minute sometimes as FPM. Okay, then we can also write WT, which is W tangential, is equal to 33,000, and we can rearrange this equation as well if you need to find power, times H over V, where WT, lower level T, sorry, WT is equal to pound force, H is in horsepower, and V is in FPM. So the important thing here is that the 33,000 is there as a correction factor for all these units that are different. Okay, so don't think that the units won't work out because your H is in horsepower and you need to convert something. The 33,000 is there to already convert all these units. So you can use this equation outright if you have all the units correct on the right side. So just make sure you have that written somewhere. Okay, you can add it to your formula sheet or whatever it is. The other thing is, for SI units, we have that WT is equal to 60,000, and again, this is a unit conversion, times H divided by pi dn. So in SI units, they don't actually use pitch line velocity, they use RPM, and so you don't need this pitch line velocity calculation, but WT would be in units of kilonewtons, so they already convert to kilonewtons. H would be in kilowatts, not watts, and then D would be in millimeters, hence why there's a 60,000 at the top, and N would be the RPM. So not a radians per second, but it would actually be the RPM. Okay, so what we're going to do is we're going to conclude this lecture here, and in the next lecture, we're going to be applying this force analysis and these force analysis equations to different problems so that we can understand how it works, and we're going to do a bunch of different problems to learn how to make this work in an application manner. So we'll see you in the next lecture.